Hi everyone. We're on to our 3 more weeks left for our semester. So I just wanted to send you all encouragement to stay strong and stay focused. We are almost at the end. What we have in store here for today is we're going to be looking at chapter 28, looking at quantum physics. And so that might sound scary to you, but hopefully by the end of today and also the next lecture for this week, you'll have a sense of understanding around what this is all about and why this is an important part of modern technology. So just to go over some announcements for today, as mentioned, we're going to go over quantum nature and what does that actually mean. We'll talk about X-rays, we'll talk about the photoelectric effect, and then we'll get a little bit into matter waves and quantization of energy, but we're going to leave some of that for the next lecture, which will involve looking at how this quantized energy of photons actually interacts with atoms, and so causes quantum jumps, as they're called, in the energy levels of atoms. So that'll be for next time. Your Chapter 26 homework is due on Thursday, April 23rd, and the homework for Chapter 28 is due on April 30th. So that is already, both of those are up online, and I'm glad to answer questions for those during our regular meeting sessions, which are going to be online, and a Zoom link will be provided from 5 to 6 or 5 to 6:15 on Mondays and Wednesdays. All right, so carrying on, some of our goals for today is to understand how light and matter are both quantized. Well, what does that actually mean? Well, so quantized is just meaning discrete. That we're going to see that in a moment that light actually shows up in these little discrete packets of energy, whereas everything that I told you before, lies. I was telling you that light was an electromagnetic wave, and now I'm telling you that it's a little packet of energy. Which one is it? Well, the question is not actually so well posed, actually, as far as which one is it, but rather that there is a dual nature of light, and there's also a dual nature of matter, and this is something that was not easy for us to see as humans, but I think that we're now more clear on this, and we've even been able to integrate this into a lot of devices, including your smartphone. So the point here is that both matter, say for example electrons or atoms, and light behave both as waves and particles, and we'll see some specific examples of what that actually means. So just to also overview, we're going to be taking a look at something called the photoelectric effect, and I will be doing some demonstrations of this to give you an idea how this works. So this is the effect that Albert Einstein won the Nobel Prize for. It's not always known by people that this is actually the very first thing that he became famous for, and that he became famous later for this theory of relativity, which we'll actually cover later, which is chapter 27. I should just mention that we've skipped chapter 27, and we will be moving back to that at the very last week. So then, looking forward, we'll also see that how electrons are quantized. In other words, they show up in discrete packets or discrete ways of looking at the waves of electrons. And we'll also see that the energy levels of these electrons and atoms are discretized or quantized. And so we'll take a look at all these effects, but I wanted to give you a little overview as far as what are we going to be looking at here. So in other words, I guess maybe summarize here is that here we're seeing that light has a particle nature, and here, especially looking at the matter, we think of like electrons as being particles, but this is actually looking at the wave nature of these electrons. So in other words, there's sort of a bending of our definitions that's happening here. Okay. So I'll just briefly go over an effect called X-ray diffraction. This shows up in the very first section of chapter 28. And I guess what's important to notice here is that, like, kind of big overview picture here is like, what is this actually, what does X-ray diffraction actually tell us? Well, if you take a look into the first bits of chapter 28, you see these experiments with X-rays, and you know about sending X-rays to your hand, for example, and the bones will block the X-rays, but the light that doesn't get through the bones hits a photographic plate, and the image that's left behind is sort of a shadow of your bones. So X-rays seem like, okay, they're useful, but what else can they tell us? Well, it turns out that when you send some X-rays into a crystalline material, so say I had a little piece of crystal and I sent in some X-rays into it, then these X-rays will diffract, which seems a little weird, right? Because we covered diffraction from before, and just to cut to the video here, we looked at this situation before where we sent in light. So imagine we have like a laser pointer, right? Here's my laser pointer, and we saw before things like having a double slit, right? And we saw that what happens is that you get a central peak here, and then you get another peak, and then you get another peak, and so on, and then it shows up on the other side kind of symmetrically, right? And so you've seen this kind of thing before, that you see it, and then the light all kind of goes this way, and then you get this intensity pattern. So in other words, more photons go here. That's going to be our first order diffraction. Some photons also go here. That's our second order, and then here's our 0th order. So this is just to remind you how, this might be m equals to -1, m equals to -2. Okay, so you've seen this kind of behavior before for whether this is a two slit, or actually it can also be sort of a multiple slits, which could be, basically a diffraction grating, right? So we saw that the diffraction grating can either be in transmission mode or it can be in reflection mode, but nonetheless, this pattern should be familiar to you. Now, here's the surprising thing. When scientists sent light into a crystal, then they actually saw the same kind of thing happening. So the interpretation is that the atoms that are in this crystal, that they actually they have kind of a bond, that maybe you've done this kind of thing before, where you've had sort of marshmallows as being the atoms and toothpicks as being sort of the bonds between them, and they form this sort of crystalline structure. And that model of a crystal is actually pretty close to being the right thing. So many solids have their atoms arranged in a regular crystalline lattice, and so the X-rays that actually bounce off of these atoms, it's as if each kind of group of atoms, you can see, forms a plane, and that plane is separated by a constant amount here, this d in this case, that's separated. And so what ends up happening then is that the X-rays then are either transmitted or reflected based on these planes of atoms. And so in other words, this picture may look a little complicated, but if you think about that d as being that spacing between the different planes of atoms, then this formula should look very similar here. In other words, that the Bragg condition is basically saying, oh, these planes of atoms acts just like a diffraction grating. So that's kind of strange. And this gives us some clue as to the fact that these atoms are somehow connected to each other in a crystalline structure. So so interestingly, then X-rays can be seen to diffract off of these electrons, and they do so using this grating equation, essentially. And one of the things that's interesting here is that they'll send multiple peaks, which can be then used to identify what kind of crystalline structure you're looking at. So going back to our original question then, we sort of have a formula here that is, I'll write it down in a second, so that 2d times the cosine of theta is going to be equal to m times lambda. So if I take a look here, if the wavelength is in this case 0.12 nanometers, that's 0.12. Oh, whoops! I should go to the camera here, and it's a for the m equals to 1, we saw that theta is equal to 68 degrees. Then, and this is 0.12 nanometers, so times 10 to the minus 9 meters. We can use all this information to solve for d, right? So we can say that d is equal to 1 times lambda divided by 2 times the cosine of theta. So putting all this together, that's 0.12 times 10 to the minus 9 meters divided by 2 times the cosine of 68 degrees. Let's go ahead and put that information into a calculator. So here's my calculator here, and I'll just put these numbers in. So 0.12 times 10 to the minus 9 divided by 2 times the cosine of 68 degrees. And actually, let me just make sure that I'm using degrees right now, because I was playing with things earlier. So we'll go here to, where is it here? Angle unit, degrees. Yeah, everything's good. Okay. So the result that I get here is that d is equal to 1.6 times 10 to the minus 10 meters. That's 16 nanometers is the spacing between these planes of atoms. So in other words, if I go back to the slides here, this plane and this plane are separated by about 16 nanometers, right? Same with this plane and this plane. They're also separated by 16 nanometers. Now the question doesn't just ask, hey, what's that separation? It goes a step further and says, well, what is the angle of the second order diffraction? Well, in this case, all I have to do then, going back, is I can take a look at the formula again and just change m as m equals to 2. So in other words, cosine of theta now, in this case, for the second order diffraction, I'll put a little 2 there now, is equal to 2 lambda divided by 2d. That looks right. So now it looks like the 2's cancel out, and I can say that that lambda, which is 0.12 nanometers, divided by 16 nanometers, which is my d, nanometers cancels out. I'm just going to take the ratio of these things over here, and I'll say 0.12 divided by 16 is equal to 0.008, and I'm going to take the arc cosine of that value here. And I'll get now that theta 2, this is the second order diffraction, is at 89.57 degrees. So in other words, the second order diffraction is almost at 90 degrees. So in other words, I sent in some light, oops, I'm going to make it a little bigger here, sent in some light into a crystal. So maybe here's my little crystal, something like this. And we saw that there's one that goes at 67 degrees, right? Something like this. This, what do we say, 68 degrees. And then there's another one that comes off at almost 90 degrees with respect to the going straight ahead. And that's our second order diffraction. So in other words, these are some pretty steep angles here. But nonetheless, we could devise an experiment where it actually allows us to identify then, based on these peaks here, we can actually identify what kinds of crystal structure we're actually looking at here. And so these little, what do you call them? These indices here, like these labelings, are called the Miller index. And so these basically tell us about the x, y, and z coordinates of the vector that separates these different neighboring planes. So I just wanted to give you an idea that this can be used to then characterize the types of atoms that we're working with. And so this is known as X-ray diffraction. And it also works for if you had smaller little pieces of crystals. If you had one sort of homogeneous structure like this, you might get a very, very sharp peak. But if you had a bunch of little crystals that were all oriented randomly, you'll end up getting sort of a broader, but still at the same location in terms of the angle. So that's called X-ray diffraction. Okay, now we're moving on to section 28.2, which is the photoelectric effect. And so here's a really weird thing. When you shine some light onto a metal, then electrons can actually come out of the surface. This is known as the photoelectric effect, and this is the thing that Einstein had predicted and he was awarded the Nobel Prize for this work, which was in 1905. So it's about 115 years ago. So I think what I'm going to do here is switch to a simulation, and I will put the simulation link in the comments, and also next to the announcement for this. But just to make it clear, I'm going to this website right here. This is the PHET or FET simulations, looking at the photoelectric effect. It asks you to download something. You need to have Java installed. If you're using a Mac, you can just click on it and say allow, or you can say, I think there's a thing where you can say manage exceptions, and then you can allow it. Anyway, they don't have viruses, I promise. Okay, so here's what I'm going to do. Let me turn down the intensity here, just to keep everything nice and simple. And I'm going to take away these graphs right now. And you see I still have some little electrons running around in there. Now I'm going to shine some different colors of light. You can see I can change the color of light on here, okay? And let me make it so you can see the whole thing here as we're playing around with this. Okay. So, yeah, so you can see you can see that I can change the color of light from infrared, that's low energy light, to UV light, that's very high energy light, right? So the shortest wavelengths here we can get is around 100 nanometers, and the longest wavelengths is around 1,000 nanometers, right? And so the colors here are the ones that we can see, whereas infrared and ultraviolet light, right? That's what UV means, ultraviolet, and IR means infrared. These are parts of the electromagnetic spectrum that we can't see, but we can see this part here, and you can see that. If you remember from last time, we had talked about this equation that energy is equal to H times F. And this H is called Planck's constant. And we're going to come back around to this again, Planck's constant. And it relates the energy of a photon to its frequency. So it's kind of a boring graph here. It just looks something like this, right? And that as you go to higher frequencies, you also have higher energies. So this is E is equal to HF. This is saying that the slope of this line, right, is equal to H, right? And this is what relates the frequency to the energy. And also you can write this as HC over lambda, because we know that F is equal to C over lambda according to our wave equation. In other words, maybe one thing you can write down is C, F, and lambda as this sort of triangle here. Maybe this is a mnemonic that's helpful for some of you. So if you wanted F, you can say it's C over lambda. If you want lambda, it's C over F. And if you want C, it's F times lambda, because they're next to each other. So this is kind of a mnemonic for remembering that relationship here. Okay, very good. So this is our way of visualizing how energy and wavelength are related to each other. Now let's take a look at the simulation here. So what this simulation is trying to help us to realize is that light is not just waves, right? That it comes in these little packets. And so we need some evidence to believe this, right? You shouldn't just believe somebody because they told you so, right? Maybe you even believed somebody when they told you that the earth was round. Ha ha ha. So the evidence here is that if you change the color, that's going to have something to do with whether or not electrons get out. So I'm going to change the intensity. I'm going to make it really super intense right now. And you see that even though I made it super intense, well, I don't see anything happening. There's no electrons coming out. But if I change the wavelength here to a certain value, now I'm making it higher and higher energy as I'm going to shorter wavelengths. And as I get past a certain threshold, electrons start popping out. And they start coming out, and they strike these plates here. And when they do strike the plate, then I can actually measure some current. And if I make the wavelength even shorter, you start to get a real measurable amount of current. There's actually a lot of electrons that start coming out. Now if I go to UV light, notice how some of the electrons are going a lot faster now, right? And if I keep waiting, then those electrons are going to go very, very fast, and I'll get a lot of current that's going through here because I'm releasing a lot of electrons from this metal, and then it's completing a circuit, which, okay, I can measure this current, and then based on that, I can make some inferences. So, did you notice that if I had the light at 565 or so, these are just the leftover electrons, but now if I'm changing the intensity up or down, it doesn't make any difference. But if I have the wavelength here, the intensity going higher makes more of these electrons. And let me maybe reset. No, it's not possible to reset. Okay, that's all right. Is it possible to reset? Okay, that's okay. So if I go to UV light, then if I turned off the light, right? So these are the leftover electrons that we ejected a long time ago, right? If I turn the intensity down, there's nothing, right? And if I turn the intensity back up again, then I start shooting out these fast electrons. Now notice they don't all go at the same speed, but on average they're faster than if I were to make them at this, say, 500 nanometers here. So if I made them at 500 nanometers, and they're a little bit on the slow side, make the intensity a little higher so you can see more of them. But making it more intense light doesn't actually make the electrons go faster. Okay, so this is all kind of like some things that we're noticing, and I'd like to encourage all of you to take a little time to play with this simulation and see what you notice. If you change the wavelength, does that change things? If you change the intensity, does that change things? Well, you have to kind of play with it to make some sense of how this is working. But one of the things that I want you to notice here is that at long wavelengths, no matter how intense the light is, we can't get any light to eject these electrons out. And when we scan the wavelength, once the wavelength gets short enough, then we start to see electrons actually being ejected out. So those are some of our noticings so far. So what are we doing here? Well, this is kind of a pictorial demonstration of the experiment, the same thing that you just saw. Light comes in, maybe it's into a glass bulb that sort of protects the experiment from having other atoms around. And we can then measure a current on this ammeter if there is any current that's going through. So in other words, the electrons are going to go down and, sort of in a, in a clockwise fashion. But of course that means that the conventional current is going to go in a counterclockwise fashion. So in other words, what's weird about this is that if you just look at it, a plate, another plate, and then a battery connected to it, or maybe even not a battery, but just an ammeter, it's not really a complete circuit, right? So somehow the light is completing the circuit. In other words, that there is light hitting this plate, ejecting electrons out, and then that's what's actually allowing us to measure some current. So far you should be like, wow, that's kind of weird, right? That's different than we saw before, right? So here's, in sort of a pictorial way, what we saw already is that as we change the frequency to higher and higher frequency, that is to say, as we change the wavelength to be shorter and shorter, there was no current, no current, no current, and then the moment that we hit that special frequency or that special wavelength, then we started to see some current going through. So in other words, and then the more intensity than we had at that point, then we got more current. But the thing is, like, even if we were down here, no matter how intense the light is, we saw that we couldn't get any current. So that's interesting. So this value of the threshold frequency actually depends upon the metal which the cathode is made from, and we'll get to that in a moment. So here's this sort of mental model of the photoelectric effect. Everyone's probably had an experience of throwing a rock into a pool, right? Maybe a lake or a pond or stream, and you throw a little rock in, and you might say, well, how much energy does it take to actually remove a drop of water and get it out of the pool, right? So technically speaking, if a little drop of water had a mass m, then you'd have to basically send in mgh worth of energy in order to get that little mass to get up and over the lip of the pool, right? So if you had a water molecule that was way down below, you're just going to have to give it more energy to get out of the pool. So the minimum amount of energy needed to lift the water molecule at the very top this is what we call as the work function. So in other words, so for the metal, we're saying what is the least amount of energy that I need to put into the system before I can kick an electron out of this thing. That's the analogy, is kicking an electron out of literally out of the metal, so that it can then fly across the screen like you saw. So we're going to introduce some vocabulary. A monochromic beam, so chromos means color and mono means singular. So in a monochromatic beam of photons, all the photons have the same energy. So in other words, if we increase the intensity of the light, we're only increasing the number of photons. And so in Einstein's theory of how this all works, then we're basically saying that electrons will absorb the energy of a photon. Then the photon suddenly like stops existing, and the electron now has picked up that energy. So we got a transfer of energy from light energy to the energy of this electron. And then in this theory, the work function is the minimum energy that's needed to get an electron out through the surface of the material. So I'm going to try an experiment here with you. Let's actually figure out what is that minimum energy that we need for this. This target here is sodium. Let's take a look at sodium. I'm going to keep scanning. I'm making higher frequency. That means lower wavelength. Continuing. Oh, so it was somewhere around, I don't know exactly. Let's see. 541 didn't do it. 538, maybe started yet 538. I'd say 538 sounds like the right one. Okay, good. So now we have to figure out what was that energy that allowed us to start getting electrons out if it was 538 nanometers. So I'm going to say this. The longest wavelength, or aka the lowest frequency that we could eject electrons, I'll just say electrons, from sodium, we found out experimentally, right, in our little simulated experiment here, that lambda was equal to 538 nanometers. Now, if you look back to our energy relationship here, right, we see that energy is equal to hc over lambda. Okay, so let's go ahead and use that expression here. Energy is equal to hc over lambda. Well, this Planck's constant is 6.626 times 10 to the minus 34, and the units are going to be joules times seconds. The speed of light is 3 times 10 to the 8th, and that's meters per second. And then wavelength we found was 538 times 10 to the minus 9 meters. So we got the meters and meters canceling out. We got 1 over seconds with seconds canceling out. And we're left with some numbers that we can actually plug into a calculator and see what happens. So here's my numbers. We have 6.626 times 10 to the minus 34. Crazy small number, right? But that's this Planck's constant. Times 3 times 10 to the 8. And then we're dividing by 538 times 10 to the minus 9. Okay, so the value that I get is actually 3.7 times 10 to the minus 19 joules. Now, that seems like a very small amount of joules if you compare it to something like where we did boxes going up and down hills and cars and things like that, right? Joules, and even like electrical bills that we talked about briefly in this class, like that's a pretty small number. It turns out that we can actually convert this number into electron volts. So in other words, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And so if that's true, I can take this number here, 3.7 times 10 to the minus 19, and I can multiply it by 1 eV divided by 1.6 times 10 to the minus 19 joules. You might notice that you've seen this number before because it's the charge of the electron. I won't get into that detail right now, but the joules cancels out, and we can actually take this number and divide by 1.6 times 10 to the minus 19, and we get that it's 2.3, it's 2.31 in our case, right? Electron volts, right? So this is going to be what we call as the work function. Or in other words, E naught, right? Is what we're going to be calling this here. So the E naught is the work function. That means that if we had a color of light that has a wavelength that's shorter than 538 nanometers, then it will kick out some electrons. In other words, if it's high enough energy. But if it's too long of a wavelength, in other words, the energy of that photon is less than 231, no dice. We're not going to get any electrons kicked out. So in other words, here's what we can expect, is that as I have low energy, if I scan that past that value, we start to see that the energy of the photons gets really big. So that's what this graph means here. We can see this graph, and then if we're right at this little threshold place right here, right, this particular place right here, this frequency, we actually see that we're not actually getting any electrons out. And so that represents, for us, that it represents our work function. Okay, so let's see how we did then. If this work function is E naught, then we found for sodium this 2.3 electron volts, right? That's how much we think that it takes to get this electron out of the surface of this material. So here's a table, and this is also shown in your book here. That's on, what is that, page 991? That's, it has the work functions for different metals. And if we look here for potassium, we find that it's 2.3. Oh, this is sodium, huh? Okay, what's going on? Let's see here. Well, guess what? Your book is wrong. On this one example that I picked, the work function is actually, for sodium and potassium, are actually very similar to each other. All the references I checked said 2.28. There's a typo in your book. So please note, you could even draw it in there on page 991, that sodium has a work function of 2.28, which is very similar to potassium. So nonetheless, we got there by crossing through this threshold that's longer than, say, 538 nanometers. We weren't seeing any light go through, but shorter than, we weren't seeing any electrons ejected, but shorter than that, we were seeing electrons ejected. Okay. So there's another idea, which is that, okay, so if the photon energy is bigger than this work function, well, what happens to the rest of that energy? And so maybe I'll draw sort of a picture here. Go back to this camera. That, in other words, in that swimming pool analogy, you know, here's the swimming pool, here's like the level, and here's the electron that can just barely get out, right? It needs to have this work function E naught to get through. But let's say that you sent in a photon, right, that has some energy of our photon that's bigger than the energy naught, right? Well, what happens to the rest of that energy? Well, the rest of that energy becomes kinetic energy. That is to say, a half mv squared, right? We'll call this K energy, right? And since this photon could go down and get another electron that's even lower, well, then that would mean that there would be more energy given to that electron and there would be less kinetic energy. So we'll call the maximum amount of kinetic energy for the electron that happens to be at the surface, gets out, and then has all this extra kinetic energy left over. So in other words, written in math words, the photon energy is going to be equal to E naught plus whatever's left over is going to be the kinetic energy. And we'll say that this is the maximum amount of kinetic energy that we can measure. And so we'll see that in a moment that this is actually interesting because we can use that little battery down there to sort of figure out what that kinetic energy is. So in other words, this photon energy, in other words, HF, has to, it's not divided by, it's just simply, that is HF of the photon, right? So HF is the photon energy. And that provides you, hopefully, it has enough so that it's bigger than E naught, that work function, and then the rest becomes kinetic energy. So in other words, if HF is less than E naught, no electrons will be ejected at all. We saw that. But if HF is bigger than E naught, then we'll see that the least tightly attached electrons will obey HF is equal to E naught plus the kinetic energy max. Okay. So here's some of the things that we saw. If we had a long wavelength, in other words, if we have an increase in the intensity of light, then more electrons will be ejected, but the kinetic energy maximum will not change. Let's just take a look at that again. So here I have UV light, and I'm changing the intensity so that there's not as many electrons that come out, but notice that they're all basically going at the same speed. And I take them to a higher intensity, same speeds, but there's more of them. Okay. Second part, if the frequency of the light is increased, then the maximum kinetic energy will increase. And so here I'll show you that again. Actually, I'm going to change this battery back down to 0. We'll get to the battery in just a second. So here's kind of normal mode here. You can see this is the speed of our electrons. If I change the intensity, here, let me wait to those little, actually, you know what? I'm going to show you only the highest energy electrons for right now. I'll wait till these guys get to the end here. That way you can kind of see the point, not just a spread of these electron energies. So here's all those fast electrons. Make my intensity higher, same speed of the electrons. They're not going any faster or any slower, right? Takes about 2 or 3 seconds for it to get across. But now if I go down to low intensities, I'm not getting as many electrons that are flying out, but they're still going at the same speed. Now if I change the frequency to be an even higher frequency, then these electrons shoot out at a much higher speed. So that's the point there, is that the electrons coming out come at a higher speed. And you can notice here as I'm dragging this along, you're actually seeing how we're changing the frequency. There's no electrons, and then suddenly it bends and it goes up this trajectory here. Okay, and then lastly, if the frequency is less than this cutoff energy, then no electrons will be ejected at all. So let's take a look, see if you can test your understanding here of the photoelectric effect. Please pause here, and maybe if you're watching this with someone in the class, just see if you can put together the facts to understand this part. Okay, so we're back, and if you had guessed answer A, then you were correct. Why is A the correct answer here? If the photoelectric in the photoelectric effect experiment, why does a red light not cause the emission of an electron through this little light can? Well, okay, maybe this seems a little bit weird to call it a blue light can. So, well, why don't we say it like this instead? Why does it not cause the emission of electron? Oh my gosh, sorry, I read the question wrong. Even though blue light can, I read it as through the blue light can, and I was like, oh no, there's a typo here. Oh gosh. Okay. All right, so even though the blue light can. So the answer is that the photons of these red lights, they just don't have enough energy to eject an electron. And we saw that through the Einstein's relationship that E is equal to HF, right? So that's telling us that even if you had a lot of those photons, then an electron can only take in that one electron, and so it simply doesn't have enough energy to eject the electron. So here is a nice summary of the photoelectric experiment. Suppose that the work function of potassium is 2 electron volts. It's not quite right, but let's just say for this example that it's 2. Then if you had 700 nanometer light, that's in the red, that's 1.77 nanometers. Doesn't matter how many electrons you send, you're not going to get any electrons. Sorry, it doesn't matter how many photons you send, and you're not going to get any electrons kicked out. Now we crank the dial so we make it a lower, shorter wavelength, or in other words, a higher frequency. And now this 2.25 is bigger than the 2.0 electron volts needed for this particular metal. And so we do start to get electrons out. They're going at a pretty fast speed. Now, if you make the wavelength shorter, and you can see here with this purple, the wavelength is depicted as even shorter, that means that the energy is even higher, and we not only get the electron out, but we also get it with a higher speed. And that is the basic idea of the photoelectric effect. So here's Einstein's explanation, is that one thing that people were playing with is they were like, well, maybe like heating the metal will cause the metal to emit electrons. But the issue that they found was that it doesn't actually, you know how like if you try to like heat up, I don't know, metal or water, it usually takes some time. But what they found in these experiments was that these electrons came out exactly at the moment that the photons hit the metal. So that clearly became, it wasn't heating that was actually causing the issue. And then the other hypothesis people had was, well, okay, so maybe it's just the matter of how much energy you're sending in, you know, with regards to these waves. And but the problem was is that if you had this low frequency, in other words, long wavelength, then you should just be able to you should be able to crank up the intensity, and you should be able to get electrons to come out, but they could not. So finally, Einstein explained this photoelectric effect by saying that there was actually the electrons started to jiggle in a very special way, so that if you sent in a frequency f for the photon, it had a frequency f, then the atoms could be jiggling at a frequency 8, or sorry, they could be promoted to an energy HF or 2HF or 3HF, but nowhere in between. So 1.5 wasn't an option, right? And this Planck's constant, which you may need to use for your homeworks, is going to be either written in joule seconds or EV seconds here. So this relationship then between the energy of a photon and the frequency is a very important one, actually, for understanding the energy of a photon. Let's take a look at our understanding once more. So in the photoelectric effect experiment, we increased the frequency of the light. What change did we see? So hopefully you remember that when you change the frequency of light, but you kept the intensity constant, then the emitted electrons were faster. And I would like to encourage all of you to take the time to try that experiment out yourself using the simulation. Okay, let's take a look at some real data and see if we can make sense of it. So I have here, I was just playing with something, so let me go to the next slide. So we have here the photoelectric effect, some data that was taken as the person was going to higher and higher frequencies. See if we can copy and paste that into here to make things go a little faster. So this is the frequency. Here's what I'm going to do. I'm going to actually just see equals to this times 10 to the 14 hertz. And there's my data. So this is going to be my frequency, and this is going to be my energy. And I'd like to make a quick plot of this here. And you can see here that if it's really true that if this equation is really true, that HF, right, is equal to E naught plus the kinetic energy maximum, then we should be able to relate then the HF to E naught and KE max. So in other words, let's go back here to this equation, and if I fit a line to this here, add a trend line, more options, show the equation on the chart, we'll see here that this gives me, this is the data from our experiment that we tried, but it's just been collected for us. So this line goes down, right? So this x-axis is the frequency, the y-axis is the energy. And we notice that at zero frequency, right, we have this sort of minus 2.3. Well, that minus 2.3 is actually our work function. So that's interesting that we can actually extract that from there. The Planck's constant is going to be our slope. And one of the things that we can do here is I'll just compare that number to this one here, 4.14 times 10 to the minus 15 electron volts times seconds. And so that is this number here. I think we can do some things here to, how does this work? I always kind of forget how to do some of these things here. Maybe more options, and then, oh gosh, I can't remember how to, I just want to show like more precision here. This is one of the reasons why I don't like Excel as much. Okay, well, I don't know. We'll just call it good. That number is Planck's constant okay, that number is Planck's constant here. Is this 4.14 times 10 to the minus 15 eV times seconds. And that corresponds to the situation where if F is equal to 0, then that's 0 is equal to E naught plus kinetic energy max. And so in other words, we'll see here that this that the KE max is equal to minus E naught, right? And so in other words, that intercept there is going to be equals to the work function of the material. Okay, and okay, so another thing that I'll then, okay, oh sorry, and then, so then the cutoff frequency then for this material, if we look over at this chart here, we can see, we can actually take a look at this equation here, and we can solve, well, we can draw the line and see where does it actually cross 0, right? That's going to be, once this line goes down and hits this place right here, then it's going to be flat for the rest of this time here. So I'm going to guess that this is about, it's about 6 times 10 to the 14. And so if the frequency is equal to 6 times 10 to the 14 hertz, then we can say that the energy is that, oh, sorry, what did we say here? This the cutoff frequency, yeah, it's about 6 times 10 to the 14. The other way that we could do this here is we could say, I'm going to set y equals to 0, and so that is going to be HF, sorry, minus 2.3 equals to 0. Oops. And so that's setting the y equals to 0. And then I can solve here for HF is equal to minus 2.3, or F is equal to minus 2.3 divided by H. And this is EV. And this H here is 4.15 times 10 to the minus 15 EV times seconds. And so if we plug that all in together, here we'll use a calculator here, that's 2.3 divided by 4.15 times 10 to the minus 15. That, in other words, is F equals to 5.5 times 10 to the 14, 1 over seconds, which is hertz. So this is going to be our cutoff frequency in this case here for this problem. Okay, very good. So, so we figured out Planck's constant, that's the slope of that line. We figured out the work function for sodium is 2.3, that's when we set F equals to 0. And we figured out the cutoff frequency for sodium, which is when Y equals to 0. Okay, so our last problem here is to look at the number of photons that we can actually see with our eyes. So I'll write down some numbers as we describe the problem here. When the wavelength is equal to 510 nanometers, the wavelength maximum sensitivity to our eye, that's around green, then if our eye is adapted to the dark, in other words, you've turned off the lights for a little while so your eyes get adjusted, we can sense a little pulse, about 1/10 of a second of light, that has a total amount of energy equals to 4 times 10 to the minus 17 joules. If 60% of the light is lost due to reflection and absorption by the tissues of the eye, how many photons actually reach the retina from this flash? Well, one thing we could do here is to say, well, I'm going to have this energy here, and I'd like to know how many photons that actually is. So let's just say that we're going to have to, since only 60% is lost, or 60%. Oh wait, what did I say here? Sorry, 60% is lost. Then we're going to have to say that we're asked the question, how many photons actually reach the retina? So that's going to be 40% of this amount of energy, 4 times 10 to the minus 17 joules, is actually the energy that reaches the retina. So in other words, just bringing out my calculator then that is going to be 0.4 times 4e minus 17. So in other words, we have 1.6 times 10 to the minus 17 joules, and we need to relate that to actually the number of photons. So we're going to use the number of photons times HF, or in other words, the number of photons times HC divided by lambda, using that relationship between F and lambda. So in other words, we can move this wavelength, the C, and this H over to the other side. So in other words, N is going to be equal to lambda times that energy divided by HC. So in other words, lambda is 510, give you a little more paper here, times 10 to the minus 9 meters times energy, which is 1.6 times 10 to the minus 17 joules. And we're dividing by H, which in SI units is 6.626 times 10 to the minus 34. That's joules times seconds. And the speed of light, which is 3 times 10 to the 8th meters per second. So we have joules, joules. This is meters, meters, meters. And then seconds, 1 over seconds, canceled with seconds. And so there's no units left. It's just a number of photons. Well, let's go ahead and put all those numbers in and see how many photons your eye can actually see. So 510 times 10 to the minus 9 times that 1.6 times 10 to the minus 17 divided by, notice that I keep those parentheses there to make sure everything's in the bottom, 6.626 times 10 to the minus 34 times 3 times 10 to the 8th. 41 photons. So approximately 41 photons is what you can actually see. Crazy, huh? Your eye can see 41 photons. That's a very, very small number of photons, and your eye can actually see that. You have a pretty good sensitive device for measuring photons. Now, actually, I just remembered that I had, going back to the photoelectric effect, that I had left out one little piece of information, which is this battery that was in the circuit. So let's just go back to that. So hopefully things are making now sense in terms of this equation. And so let's imagine that I do, going back to this equation here, I do have more than enough energy to exceed the threshold, right, of this I have more than enough energy to exceed the threshold of the work function. And I'd like to basically take these, so I have all these electrons. Some of them are slower because those are coming from a deeper place in the metal, and some of them are faster. And I'm going to take this battery and flip it around, and I'm going to basically do, if I go this way, I speed everything up more. But if I go the opposite direction, I slow everything down more, and you see that the current is actually dropping here. And if I go more in the negative direction, the current's dropping, the current's dropping, the current's dropping. And then at around minus 2.2, the highest energy of electrons, they just barely make it to this plate, and then they turn back around and come out. So in other words, there's no current that's actually completed the circuit here. So that's an interesting situation, that we can actually tune this battery, and we can actually do that and figure out then what's the maximum amount of kinetic energy that we have in our metal here. So that's also kind of interesting, but it's another aspect of looking at this experiment. And you're basically what you're doing in that case here is that you are you're saying, okay, I'm going to figure out. Let's look back to the paper here. If we have the formula here that HF of my photons, let me just copy it directly from the slides here, is equal to KE max plus E naught. Okay. Then we could say that the amount of energy minus E naught is going to be equal to the maximum kinetic energy. And I know that if I have between these two plates here, if I have, so these electrons are trying to go this way, right? And if I hook up a battery that puts a bunch of negative charges on this side and a bunch of positive charges on this side, then I'm actually basically allowing them only to go up to this place and turn right back around and come back to this plate. If I can tune them such that Q delta V, so here's the battery delta voltage, is equal to KE max, right? In that moment, then I'm actually going to take the highest energy electrons, and they won't be able to sort of make it up the so-called hill that they would have to overcome to complete a circuit and measure current. So they'd be sent back. So in other words, I can tune that battery and use that as a way to measure the work function also. So that's just kind of another aspect of this experiment that I wanted to share with you. Okay, so hopefully photoelectric effects making some sense. If it is not, I want to recommend to you to spend some time with this simulation and play with the different graphs here and see if they can make sense to you. So as I change the intensity here from high to low, so for example here's from high to low, you can see that when you get to zero intensity you have no current, and then if you're at least you're above the threshold, then you'll start to see more current for more intensity. If you try changing the frequency, then you're gonna hit a moment where there's no energy of these electrons. In other words, they're not being ejected. And if you go above the threshold frequency, then you actually start to see energized electrons. So those are the things that I'd like for you to focus on. You can also try doing some different materials and see if you can figure out what their work function is based on the experiments. And so the whole point of this, right? What is the whole point of this photoelectric effect experiment? Is to tell us that light comes in these little packets called photons, right? And so in other words, that light is quantized. It's not just a wave, but it actually has a photon nature to it. So in other words, light can be described now as photons. Next time, we'll be taking a look at the double slit experiment, which you've seen before in a classical way, but we'll be looking at it in a quantum mechanical way. See you next time.